let's start.
Excellent. So yeah, maybe just to add, I'm very glad that so many of you registered, and it's very nice also to see that there's like really people using Picterra since a very long time. That I guess are quite really interesting in that application, and then also quite a lot of other players from the geospatial ecosystem. So I think we have quite a mix of people here, which is very interesting. And so I'm pleased that you're there and attending. And so I hope you will enjoy it also. So just very quickly for the ones less familiar, let's say with Picterra, very briefly. So we are a web platform that basically allows you in a very autonomous way to train and deploy deep learning models to extract information, geospatial information from your imagery. The idea is that you can extremely quickly start to train a model, and that also in terms of investment, in terms of investment time and cost that you have to make, this also scales with your project. So you can start with something very small and then make it scale, and finally integrate this into your flow, your applications. So today in the agenda, we just get back a little bit on why building direction is something that matters, is something important, and how Earth observation and machine learning enters into that can help on that. And then dig a bit further on what Picterra is bringing for that specific topic. And we will see really like real life use cases with our invited speakers. So from GET, they are based in Athens. So there's Gabriel and Georgia here, and they will also walk you through a real use case. It will be very interesting. And we'll finish with a live demo from Roger. So going also live on the platform, showing you different things around that topic. And in the end, a Q&A session. So a lot of you actually asked us some questions on when you registered. So we grouped a bit them and we'll answer that. And also, don't hesitate to write in the chat. So if you have questions, then we will collect that and we'll try to answer them at the end. So why is it so important to detect and map buildings? So just to bring this back, I mean, buildings are there as something that basically translates about the cities, about the population, and this is key for many things, among which just knowing about the population. So census, for instance, at the national level, you really need, for instance, to have this building information. You have all the urban planning, policy meetings, or these things at large scale, where you need to have the localization of your buildings, which translates into basically mapping the population. Next to this, there's of course all the key infrastructure, so being the public transport or the distribution networks of water, electricity, postal services. So all these elements really rely on an accurate mapping of the population. And finally, you really need also to have this information in a very up-to-date fashion when you are in a disaster situation, either to mitigate the risks beforehand or to have a rapid response or emergency relief. You need to have this information. Where is the population? How can you organize the relief operations? And then also something that resonates also a bit differently in different situations. But these are vaccination campaigns, mainly in developing countries where you may not have a base cadastral information. You need to have a way to organize those. So we'll see also a quick use case on that. So all this observation comes in the game. So of course, as we may not all be familiar, depending on from which country we come. We may have a lot of cadastral information available, but this is really varying over the planet, and there is many places where there might be an information, but maybe not accessible. There might be an information, but not up to date, and there's many places still where the information is even not existing at the level of an individual building. So to do this from the ground, I mean, this is traditional surveying methods, and this is extremely time consuming. So that's something you want to avoid. At the moment, you want to do this at a certain frequency, and that you need this information also in short time lapse. So that's something very up to date. You cannot wait for several years to get that information. You need to do this remotely, and that's where remote sensing and Earth observation comes in the game. So what we have at hand, so of course, this variety of sensors from the drone to the satellites, and this basically brings you from sub-centimeter resolution up to meter and above. And of course, from this, you can get very different information. So actually, the range into which you can deal with buildings can go actually already from 10 meters, where you will be mainly able to map urban areas. So yeah, building areas. You will have difficulties to catch the individual buildings if they are too small. Once you move down towards the meter resolution, you will start to be able to localize individual buildings, but that doesn't mean that you get the building footprint. In order to move to the building footprint, you will have to go in a sub-meter resolution, 50 centimeters, 30 centimeters, where you will really be able to get this boundary of the building, which, depending on the application, you need. And then finally, once you move to higher resolution, which are then not obtained by satellites, this is useful once you want to characterize the building. So putting a category, being able to know what is on the roof. So these are the different elements that you need to know in order to choose the platform. It really depends on the end information we need. So really from purely localizing to mapping precise footprints and then characterizing. So just here to mention back that actually, how do you get data and how can you really easily plug data in your analysis? So you can very easily connect some of the free satellite data available, such as Sentinel, on the platform. You can also access some of the satellite and aerial images that are available, so it may fit to what you want to do. This is also great ways to understand which resolution you need, so you can have a look, see if that's the data you need or not. And then I wanted to mention specifically here, Open Area Map. So this is an open repository of aerial images. You have also some satellite images there that people brings in, and you can actually browse over the globe on these different images, and you can very easily import it on Picterra. So we're actually working with OpenAI in order to make it even simpler, but today the way to work with it is that you can copy this image URL, this TMS link, and then simply enter it on the platform and in this custom URL remote map import. And from there, you can then browse the data, import all of it or some pieces, and directly work on Picterra. So no upload, download involved on that. Finally, I'm very happy to be able to mention you this, and this is something that will also be extremely powerful for your next, let's say, project with Picterra. You will be able now to actually browse satellite imagery and even buy them directly from the app. So here I'll show you just this small screenshot, and you will be able to access this already since from next week on. You will be able, for a certain zone, certain date range, be able to browse some satellite archives, and from there directly see the price and be able then to buy it. Next step will be for you to be able to buy new images, and this will come later on, but that's definitely on our roadmap. Finally, you may have some subscriptions available for data, so that's something we wanted to highlight also. Some of you might already be using some of the providers like Airbus or Digital Globe for mapping buildings. If you have a subscription, for instance, Secure Watch, which is a base map, or you have the One Atlas base map, these are basically possible to be connected to Picterra. So this is something you can actually really do. So if you have any doubt about this, you can simply contact us, and we will how to do this very easily. Finally, the idea is that also you may want to do something more repetitive, something programmatic in order to really do some monitoring or repeated tasks. There is the public API that you can use. So you can connect your data source, you can on the app train your model, and once you have it trained, simply call it to the API and deploy it to your data. And we have, of course, a Python library on top of that, and a JavaScript library that should come soon. So I'll pass over now to Roger, that will dig a bit further into the specificities of Picterra in this context of building selection mapping.
Okay. So the question I would like to answer for you is, why should you choose Picterra for building detection and mapping? And in order to answer that question, before I get into the question of building detection at all, there's kind of a myth or about machine learning that I would like to debunk. And so there's a very first basic question I'd like to ask, which is, what is a building? And so I keep hearing people ask, oh, can you do building detection? But what does that exactly mean? There's so many types of buildings. There's American-style buildings in suburbs, which are nicely spaced out. There's European Old Town-style buildings, which are much closer and oftentimes touching each other. Slums and informal settlements, those also count as buildings too. And then there's also different types of buildings in different industrial factories, or sheds or huts for agricultural use cases. And in addition, all these types of buildings can appear in different geographies with different backgrounds, and can also be visualized using different sensor types, even height maps or NDVI or SAR, and across lots of different resolutions. And so a building in an image can appear very different depending on your use case. Here's a few visual examples of what classifies as a building. And as you can see in each of these images, they're quite different from each other. The quality of the data differs quite a bit in resolution. Some of them are a bit more hazy. In the right one, the buildings aren't touching at all, but in the second one, they're all touching each other. So there's really a large variety of ways to define a building. Here are some more buildings that were created with the different sensor types. And so on the left, there's infrared. In the middle, there's a height map, DHM. And on the right, there's SAR imagery. And so people oftentimes ask us, can Picterra do processing with anything besides RGB imagery? And the answer is yes, because to us, whether you're doing red, green, or blue data, or you're doing DHM data or SAR data, it's all just numbers to us. So that's all data. And one of the strengths of machine learning is that it adapts to your data. So if you provide a machine learning model with DHM data, for example, the model will adapt to the data that you provided. And I'll get back to why that's a key factor in why Picterra is so powerful. So another question that people have been asking us a lot is about whether or not we can orthogonalize building footprints. So that means taking the footprints and making sure all the corners are perfectly perpendicular. And well, I have to say this is kind of a difficult case, because as you can see from this image here on the left, the building certainly does have right angles. However, in the middle, the building does not have right angles at all. So in that case, you do not want to orthogonalize the edge. And in the extreme case on the right-hand side, the building actually has a curved boundary. And so there are ways that you can put constraints on the model itself so that the outputs do follow certain shape guidelines. However, this sort of defeats the main strength of machine learning, which is its flexibility. You're basically adding constraints to something that is super flexible. What can be done, however, is once you have the outputs generated by your model, you can apply your geometric rules of shape or whatnot on the detections. And this is more of a geometrical operation that can be done after the machine learning model. So it's more of like a fix-up or a cleanup. It happens after the machine learning model, not within. And that keeps the machine learning model very flexible to whatever type of data you provide it. But then you can add on this cleanup, this geometric processing afterwards. And so one final thing that makes buildings different from each other is not only in the visual appearance of buildings, but people's understanding of what a building is. So in this case, some people might say that this is 3 separate buildings. However, they also share the same balconies and they're sort of connected. So someone else might say they're all the same building. And maybe you want to include the balconies in the footprint, maybe you don't. And so there's all these different definitions of what a building is. So when someone tells you they have building detection, what does that actually mean? So let's bring this all back to machine learning. So how can machine learning be used to solve this problem of all these different building types? Well, basically machine learning can learn from image content and outlines of buildings on those images. That's it. That's all you really need. And the core algorithm, in our case, which is a deep learning architecture, doesn't need to change to adapt to your specific building detection scenario. What really needs to change is, as I said before, the data. And so what you need is you need the right data and you need a platform to be able to easily create this data and feed that data into an adaptable, flexible machine learning model. And by doing this, you can create your customized solutions on a case-by-case basis. All this is going towards saying that there's no global building detector. There's no one solution that can detect all different buildings across the entire world and work for every single use case. That does not exist, period. There are different use cases, different buildings, different solutions, and therefore you need different data. And so oftentimes I see this expectation of people where they expect that all they have to do is upload their images, click run or like click a button somewhere, and all of a sudden, poof, they get buildings detections across all of their images. However, when you're clicking run, you're running a machine learning model that has been pre-trained on a lot of data, but you don't know what data that model has been trained on. And no one has a data set that has every single possible type of building or structure in the world, which, as you saw earlier, is an insane amount of variety. So the performance of said model can only be good on data that is similar to what it is trained on. However, you do not know what that data is. That data has been defined by someone else, not you. So that's what makes the Picterra platform different, because it's about you and about your needs. You can train your own models very quickly and very intuitively. And this first point is very important. We put a lot of development effort into this. We want to make sure that you can build your models very quickly and in a very easy way. And each of these models that you build on the platform solves one task, but you have the flexibility to create quickly many different models. And each of these models, of course, still works well only on the data that is similar to what you train it on. But the key thing here is that on Picterra, you are the one who defines that data, which means you are defining the scenario. In addition, you also have the flexibility to iteratively improve your model and expand its generalizability over time. So to bring this back to buildings, this means that on the platform, you can define a detector that can detect your building type over your sensor type with your resolution over your background regions of interest. And as a side note here, because this interaction is so simple on the platform, you don't have to do just buildings. You can actually put in whatever image and find whatever you want. So you can use exactly the same workflow on the platform to do roads or rivers or forests or chickens or cows or whatever you want. Basically, if you can see it in the imagery, then you can detect it with Picterra. So one question you might ask is, how easy is this to do for a non-ML expert? Like, how can you build a model if you don't know ML? So that's the nice thing about this about Picterra platform, is that for us, as long as you know your data, you know what a building looks like on your imagery, then you're good to go. You don't have to know any technical details about machine learning. You still have to put some effort into annotating the data, but this is not the same as, say, hiring a service to manually annotate all your images. These annotations are examples that are used to teach your detector how to automatically detect what you're interested in finding in the rest of your imagery. And the cost and time savings can be huge. As you can imagine, it would be maybe 1 hour of teaching yourself how to fully effectively use all the functions of the platform versus a week of manually annotating images yourself. And the natural question after this is, okay, how much data do you need to annotate to teach your models? And it depends on the complexity of your use case, but it's usually a lot less than you think. Some of our users have had use cases where they get away with as few as 10 annotations to get results. That's it. That takes about 1 minute to do. And it's not on the level of thousands or tens of thousands of annotations that you might see in academia. This is thanks to Picterra's iterative workflow, which stresses quality of annotations over quantity. And we also have a feature that we just released called base detectors, which lets you train your models on top of other trained models, which gives you basically a head start in building your own detectors. So you can produce good results with even fewer annotations. But I'll get more into that later when I give the demo. So to summarize the platform in general, it is an end-to-end geospatial machine learning platform where you can bring your own imagery or access imagery on the platform, and then you can build your own customized building detection solution using techniques such as active learning, data aggregation, low shot, and transfer learning. Except these are all technical terms, and the great thing about the platform is that you don't have to know about any of these things. These are all hidden to you. The platform is so intuitive and easy to use that you need to have zero machine learning or coding knowledge whatsoever to use it. And so now I'll pass the presentation back to Frank, who will be talking about some real-life use cases on the platform.
Excellent, thanks, Roger. Just moving the mic over. Good. Yeah, I wanted just before passing the mic to Gabriel and Georgia, I wanted to show you some of the things involving building detection mapping on Picterra. And you will see a little bit and better understand what Roger also said, this capacity of adapting to very different types of buildings. So that example I found it quite nice because it is really far away of the traditional detection of buildings of the Western type, very nicely rectangular and separated from each other. Here it's about informal settlements in Tanzania, and so you see that the idea is really to be able to map all these different roofs. So there's quite also a particular texture there, and so there you could really also do it very quickly with not that many annotations. So that really helps into mapping urban sprawl, having a little bit of monitoring on those slum areas. Another type of interesting type of buildings is what can you do when you have a building under construction? You may want to categorize the building under construction versus the one already built. So that's something you can do. You will basically do two detectors. So one where you basically train the model on these buildings without roofs, so they were just with the foundations, as you see here on top. And then you do another one where it's finished buildings that are really completed. And then you can end up with a map showing you basically the different type of buildings and really having the correct footprint. That made me think about this OpenAI challenge that occurred already more than a year ago, and that was interesting because that was co-organized with We Robotics, and they had this challenge running for 3 months, and the idea was that to develop a model for mapping these different buildings. After the challenge, actually, they started to work with Picterra, and they actually tried to redo the same thing, and it was really extremely interesting to get the feedback when they said, look, we did it actually in a few minutes. We could basically do the same as what was done during the competition. So that's really exciting. You can adapt very quickly to the problematic. Also recently, so one of the flying labs, this is also attached to the We Robotics family. So there is Dr. Huchi Saxena in India, the India Flying Labs. They started to map the slum Dharavi in India, and also there they made it adapt to this very specific type of roofs. Finally, so there was also last year some work done on refugee camps. So that's something you want to also do. So very quickly map the shelters in refugee camps. So often this is something you have to do in really rapid mapping fashion. And they did it over this Kutupalang camp in Bangladesh. So, in the end, it grown up to a size of 1 million of refugees. So that was huge. And they could really benefit from connecting the data that was on OpenAI map to Picterra and then run the detector to detect these thousands of shelters. And finally, the vaccination campaign I mentioned. So we worked with Maha, we does some mapping in this context, and in the context of Gavi, where it's the idea that once you have some point where you have early signs of infections, you want then to have a mapping on those areas in order to start to organize basically your campaign of vaccination. Also, in order to start and to communicate with the community leaders and really be sure that everyone is aware of what will be going on in the ground to avoid problems. And so finally, to mention that we are running actually a contest in the case of the COVID-19. You know, there's this original contest from Eurodata Cube and Sentinel Hub ongoing, and so we had our context on top of that. So based on this Eurodata Cube data sets, you can start to process and analyze with Picterra, and then submit what you discover from that to us, and there's some prize. So don't hesitate to have a look and register there. So I'm happy to pass to Gabriel and Georgia now the mic, and they will show you a bit their use case. I'll let you, Gabriel, introduce more Get, and then pass to Georgia. Thanks.
Hello to everybody. First of all, thank you very much, Frank, and all the team from Picterra for inviting us to this webinar. It's something that we started working a few months ago, and it's really a surprising, successful process using this solution. So we would like to share what we have found working in this topic with Georgia, who is Industrial Research Fellowship Program from Democritos. So I am the CEO of Get, and we have a very simple mission, and this mission is making location matter. So we are trying to maximize the value of the information that our partner, our customer has, and we are doing this through geospatial enabling technologies and tools that we offer, basically using open source technologies. We are offering solutions through 5 business units. The first one is GeoICT, that mainly we are offering SDIs. The second BU is open data. The third one is business intelligence solution, environment, and at the end, the Earth observation. It's well known to everybody that we are in a phase that data is one of the most valuable resources in order to take decisions. And this creates a very, very unique way of competing each other, because it's not only that we have more data, it's the fact that we are running in a situation since a few years now that Copernicus, which is a revolutionary Earth observation and monitoring program, offers the data through a policy which is open and free, available to everybody. So this innovative program creates really new opportunities that you can handle data that you can collect every day in a way that you can take a clever and immediate decision. But how can you do that? It's not so simple. So there are challenges in using the information that you get continuously. Those challenges in our company are focusing in 4 different areas. One is how you can handle data, and we are working on that using a Sentinel Hub from Synergize. And the other vertical application that we are focusing is environmental monitoring, is INSAR application, and artificial intelligence and machine learning topics. On that, among others, we are working with Picterra, and this is a challenging topic that creates very fast and in an easy way solutions that can be used, for example, in urban planning. So I'm passing the line to the microphone to Georgia in order to describe exactly what we did in this topic.
Hello, everybody. Thank you again for having us. I will tell you about how we built a buildings detector using the Picterra application for our case study, which is the Papagou-Cholargos municipality in Attica, Greece. At first, I will talk about the image that we chose. As it was stated in the Picterra website, for building detection, a minimum spatial resolution of 8 centimeters for houses and a minimum spatial resolution of 4 meters for large buildings is required. For our case study, a very large-scale orthophoto image of the Papagou-Cholargos area was used. The image is true color. It has a spatial resolution of 20 centimeters, and it covers an area of 12 square kilometers. Moving on, for the successful upload of the image, as it was stated again on the Picterra website, the user has to consider the size, the CRS, and the format of the image. So in our case, for the VLSO image, we had to reproject it from GGRS87 to WGS84, and then we had to convert it to the 8-bit RGBA format using QGIS. Then, after the preparation of the image was uploaded to the Picterra application from the My Images tab. From there, we started to create our own detectors from the My Detectors page by choosing the training new detector, where in this new detector we put our VLSO image as a training image. In the training page, we started by drawing specific training areas and annotating all the buildings objects inside them, as you can see here in these 3 images. Moreover, we draw several empty training areas that do not contain any buildings in order to show our detector what is not a building. In addition, we drew accuracy areas and annotated all the buildings objects inside them so that we can have a measure of a comparison. Then we drew the testing areas and we chose our preferred settings. In this case, we chose the detection type that we chose was count, the output type was polygon, and we also created a size filter where all objects below 10 square meters were not considered. And then we trained our detector. We saw the training results and we evaluated them. We edited the detector, and when we were happy with the detector, we decided to run it on our VLSO image for our study area. After running the image, we had 2 types of results. The first result was a vector layer containing polygons of all the detections in the Papagou-Cholargos area. And then was an analysis report that contained some statistics about these detections, which an example was the area and the count. From there, we decided to download the vector layer into GeoJSON format and insert it into QGIS for further analysis. The vector layer from the Picterra application containing the detection was inserted into QGIS and was clipped to the boundaries of the Papagou-Cholargos municipality, where we had actual buildings and we could compare it. In order to continue, the polygon validity had to be checked, and only the valid polygons were selected for further study. Then we took all the valid polygons from the Picterra building results and compared them to the actual buildings using feature count and also by seeing several areas like sport grounds and leisure areas. Overall, the detector successfully detected all the buildings in the Papagou-Cholargos areas, presenting only 5.3% of uncertainty, which was mainly due to some buildings being really close to each other, basically touching each other, causing the detector to present them as one building. Moreover, furthermore, there were small issues on parking areas, leisure areas, parks, and squares, and also some sport grounds and schoolyards. But all these small issues were also included in the uncertainty percent. We also saw that the precise detector training is really important, because in other runs that we had with Picterra and other detectors that we created using random training areas, we saw that with precise detector training, we had much better results and much less uncertainty rate. To conclude, Picterra is an excellent tool. It successfully detected all the buildings in our area and also some buildings that were not also in the Papagou-Cholargos actual buildings layer. It was very easy to use. The instructions in the website were really easy to follow. Also, we saw that it was really time effective in comparison to manually digitizing buildings data one by one. So this application can be proven very useful in several sectors, in example, like urban planning and local authorities that are interested in building detection. Thank you very much.
Thanks, Verja. Very interesting. Very nice to see something extremely concrete and also with the benchmark. So that's really great. Pass now over to Roger for the live demo.
Hey again. So Georgia did some of my job for me already, so thanks, Georgia. But I figured I'd also give you an actual live demo of the platform itself, and so you'll see some of the elements that Georgia just presented as well. So this is what you see when you first log into the platform, and you can really divide the Picterra platform into sort of three main conceptual things. There's the training of your detector, the running of your detector on your imagery, and then the viewing and managing of your results. So those are sort of the three elements you can divide the platform up into. And so here you can see on the left-hand side here, there's your detectors. And this is my own account, so I've built quite a few already, of course. And then also here are your images, where you can see all the images you've uploaded to the account. So let's get straight into the training of a detector. So there's two ways to start training. You can either train using this button right here, train a new detector, which opens up this pop-up, and you can name your detector whatsoever. There's also a new feature we just released that I talked about earlier called these base models, or here we call them pre-trained models. And as I said earlier, there's no pre-trained model that will work out of the box to detect buildings for your use case unless you're extremely lucky with your use case. However, big data and a lot of data still helps in some way. And what it does do is that it gives you a head start in building your models. So say, for example, if I select buildings right here, and I train a new detector based off of that, the model here has already been trained on various data sets of buildings, not necessarily ones that relates to your particular building use case. However, it has already some kind of knowledge of what a building roughly looks like. And that means that when you are building your detector, you can get a head start and you can create fewer annotations and build a successful detector in less time. And so let's just start with this, and let's say we wanted to just detect residential buildings. I don't have a real use case, so it's a bit broad, but these are some settings for your detector type, which I'll explain shortly. For now, we'll set it to count. So when you first create your detector, the first thing you need is an image on which you can create these training annotations to teach your detector. And so an example I'll be presenting to you today, I'll be using a small town in Switzerland called Solothurn. And so the first thing to do is to add an image to your training. And these images are actually coming from an online map imagery source, which is basically an online streaming, free online streaming imagery source, the kind that Frank talked about earlier. So I can just add to training here, and I can begin the training process. So everything I tell you here today is also in this little tutorial, which you can find on the bottom left here. And so you can always access it whenever you're in need of some help. In addition, we also have something called Picterra University, which is a series of online courses to really get you a super in-depth knowledge of how the platform works, as well as give you some conceptual information about machine learning and Earth observation, which you don't necessarily need to use the platform, but it's good to know. So we are trying to detect residential buildings here. And the first thing to do is to do something called creating a training area. And what a training area does is it specifies a region of the image that we will use to teach the model about what is and isn't a building. And so I'm going to create a training area right here for now. And basically the reason we have this is because in a traditional machine learning workflow, you might find that people will annotate an entire image and then pass it to your machine learning model for training purposes. However, in geospatial imagery, your images can have a lot of things to annotate, and you really don't need to annotate that much of it. So training areas basically lets you define a small subset of your image to use for training your detector. And here I'm starting with only a small section that has like 10 or so buildings. And so the process is basically I go to the annotation tool here and I outline these examples of the buildings. And I don't want you to wait for me to draw things. So I will move on, just pretend I annotated everything here, and I'll move on to the next step. The next thing to do is to create something called testing areas. And testing areas are basically places in the image where you will run the model and get a preview of what your results look like. So if I click the train button here, it's going to pass the information, the data that I've annotated in the training area into the model. It's going to train it, and then it's going to run detections on this area right here. And the purpose of this testing area is to give you a preview of how your model is doing and where it has weaknesses and where it needs to be improved. And so this is actually, this whole training mode, all this drawing and running a detector in your testing areas, this is all free. It doesn't charge you any of the processing credits on the platform, which means you can iterate and improve your detector over time as many times as you want to until you are satisfied with the results. After you are done training your detector, then you can move into something called detection mode. And this is the second part of the platform where you're actually running your trained models on the rest of your imagery at scale. And so let me show you what that looks like. So I already created a model before for this image. So here's the model I created earlier. And note that this took me just about 10 minutes. And after I clicked train here, I got some results within these red testing areas. And so you see these are the detections of the buildings. Some things to note about this training, about the detector actually, is that we also have some other options associated with the detector in these settings over here. And so for the case of buildings, the most interesting one is probably this output type here. And this output type is basically a post-processing step where we will turn your buildings into orthogonalized boxes. And this relates back to what I had mentioned earlier about creating corners or square corners for your detections. However, of course, this doesn't work for every single building case. As I said earlier, there are many cases where the buildings aren't square. And so if you want more than just the box type output, then that's something that you can talk to us for, and we're happy to work with you with that. Some other settings here include things like the size filter, in which you can filter out the different sizes of objects. So if there's things that are too big or too small, you can eliminate them from detections. And there's also this thing here called detection type. And that's an interesting use case, interesting setting. There are two types of detectors you can use. One is count. Basically, this works well for objects that are well separated. You can imagine the desired interaction as pointing to different objects in your imagery that you want to find. The second mode is segmentation, which is less relevant to buildings, but still good to know about. And that's for more like land use applications. So if you're trying to say, map an urban area in low resolution imagery like Sentinel, you would probably choose segmentation mode, and you would sort of get the square kilometer coverage covered by an urban area, for example, instead of counting individual buildings. So now let's move to the detection mode. So once you have trained your model here, then it's just as simple as going to your imagery here and then running your detector just by clicking this button here. And so I've already run the detector already, and so I'll show you the results on this. And so you can actually visualize results over this whole folder of images just by clicking view here. And this is one thing that we focused on in Picterra, is to make sure that your detectors work at scale. And so this image is very large, which means we've actually broken up your detections into several different detection cells. It's more for technical reasons, but basically it divides up your problem into smaller problems. And overall, we detected a large number of buildings. I think across these three images, we detected a total of 35,000 buildings. And the training of the detector took me only 10 minutes. So really not that long. As you can see here, the results are not perfect, but if I spent more time with it, I could improve it over time. And that's one of the major flexibilities with Picterra, is that you have the freedom to improve your model because it's your model. It's not a fixed entity that someone else trained for you. One other feature, So also from this view, you can download your results, and you can either download all the results across all the detection cells here using this button, and you can export in GeoJSON, CSV, KML, shapefile, whatnot. Or you can download your results per cell. You can also generate a PDF report for your project here, your folder. And this is something that we'll be expanding in the future to add more capability so that you can generate more interesting reports from your detections, things such as heat maps or things that you might see in a statistics package like Tableau, for example. So that's kind of an overview of the workflow of Picterra. As you can see, it's quite simple. It's just about training, detection, and then your results. One feature that I would like to go over, because it relates to a question that many of you asked, is something called accuracy areas. And so this goes back to training mode. And a lot of you asked about how do you determine the accuracy of your detector. And this relates back to what I said earlier about there not being a single global building detector. Just in the same way, because there's no single global building detector, there's no global accuracy that you can measure for any detector. An accuracy is based on your use case. So it's how well your detector performs on your imagery. So you have to be the one to get this accuracy. It's an accuracy associated with the detector and the images, not just the detector. And so we have this tool here called accuracy areas. And basically it works quite similarly to training areas. You outline an area of the image, and then you can outline the buildings inside this area. Imagine I outlined all of them. And what happens is that once you train your model, it will run detections inside this area, much like testing areas, and then it will compare the detections to the outlines that you drew, kind of like a scorecard, and it'll output a score of how well your detector did on that area. And so if you have enough of these scoring areas, these accuracy areas, you can get a good assessment of how your detector is doing on your imagery for your use case. This is a bit of a lightning intro to what the course does. And I can't summarize two years worth of development in the platform in 10 minutes. But if you're interested in knowing more in depth about all the features of Picterra, I encourage you to take the Picterra University course that I mentioned earlier. And we will post you guys a link on that later on after the webinar. Thanks.
Thanks, Roger. Excellent. I think now it's time to move to the Q&A session. And so I just share my screen. Basically, so there was some of the questions that we got before, and Monica collected some also from the live now. So
exactly. So so we have a few very interesting questions from you. So for example, I have a question to Roger. Could you tell us how can we deal with the orthogonalization of building footprints?
So this relates a lot to what I talked about earlier. The orthogonalization, or the squaring of buildings, is something that for us needs to happen outside of the model as a post-processing step. And so once you get your detections, they might be a little bit jagged or fuzzy, and then you use geometric operations to square those edges and make them more perfect. And as I just showed you in the platform, currently we have a built-in way of doing this, just to convert your detections to just boxes. However, if you want something a bit more complicated than that, then certainly you can contact us and we can create a solution for you to work on your specific building shape.
Thank you, Roger. I have one more question for you. Could you tell us if can non-nadir, non-looking down images can they be used? So, for example, street-level imagery such as Google Street View, can it be used in Picterra?
Right. So in fact, really, you can use any imagery you want in Picterra. So off-nadir is totally valid, but it depends a bit on your use case. So off-nadir is when your image is taken from a not quite aligned angle, so you might see like the side of the building. And certainly you can use this to detect your buildings. I wouldn't recommend it for finding the footprint of your building, however, because in that case, it's much better if you have a top-down image of your buildings, as building footprints are also top-down. But yes, you can use, if your goal is to count buildings, then certainly off-nadir images are completely valid.
Thank you very much. So now I think I have a question for Frank. Frank, could you tell our audience what spectral band type for monitoring buildings can be used?
Yeah, and the spectral band question is always, let's say, a bit up there. And what I can say for buildings, you can do a lot already just with the RGB. I mean, you're very fine. You can enhance a bit the signal if you, for instance, remove the blue band, which is usually more noisy, with the near-infrared or a short-wave infrared band. And so doing like a 3-band combination with that, like a false color, near-infrared image, could be fine, and even bring a bit things sharper in the output. But often doing this might bring you some bands which have a lower resolution. It's a trade-off.
Thanks. And one more question to you. How big is the difference between your approach, probably Picterra, and manual digitalization?
But I think Georgia mentioned it, and so we mentioned it at the beginning. I mean, in the specific case of buildings, it is very time-consuming. I mean, to annotate buildings, that's something that takes time. You will really not be able to copy one shape to another very easily. So in even simple objects, like even like detecting animals, you can maybe in a ratio like 50 to 100 times faster by just annotating to train a model and running it instead of doing it manually. So when you move to buildings, this will even be higher in terms of time gains you get.
I see. Thanks. And for disaster management, how can our users get images before the event?
Yeah, I mean that's often a question. So about how can we ensure that there will be image of an area before to do like change detection, things like that. I mean, now the way is to try to be able to quickly search through the archives of that images. So that's the thing I mentioned, that we have found on the platform. You will be able to look for one given AOI. You will be able to look, is there satellite images already taken? And then the idea is that if something happens, you can basically come back on time and buy an image for that.
Thanks. And one more question to you. Can a detector be automated to provide a weekly report?
So yeah, this idea of then that you enter into something very repetitive and you have a given task that you want to automate for very frequently. This is a typical case for using the API. So you will still have this first stage where you train the detector on some sample data that you get the accuracy you need. And then once you have this, then you need to basically integrate that in your workflow. It could be a script that is calling the API, catching the new data. So maybe if you imagine a refugee camp or like trying to detect objects on roofs or over a certain place, you will have to collect the data and then through the API you run the detector. And then from that you will basically get back the detections and you will be able to extract the number, the surface, and so from this derive some information to create a report.
I see, thank you. And maybe Roger, we also have questions which maybe you would like to answer. One of our users asked how he can build a detector, if he can build a detector for a high resolution image and then use it effectively on low resolution image.
This is a bit of a tricky case because high resolution and low resolution imagery is quite different, of course. One thing I can suggest for you to do is you can create annotations using your high resolution imagery, and then in fact you can downsample your imagery that you use into the lower resolution format, and then use the same annotations, train a model using that, and then run it on the lower resolution imagery. So that could totally work for you as well. But of course, it depends on exactly how low resolution we're talking about, because if you're trying to detect, for example, individual buildings on Sentinel, you still can't even see the individual buildings on Sentinel very well. And so, as I said earlier, the key rule is if you can see it in the imagery, then you can detect it with Picterra. So if you can't see the buildings, then that's going to be tough luck there. Of course, there's many other use cases you can do with Sentinel imagery on buildings. Just individual buildings is not one of them.
Thank you. Thank you for your answer. I also have one more. Is it possible to detect more than one feature at a time? So, for example, to detect at the same time building footprint and a swimming pool or solar panel or different objects.
So the model that we decided to use on Picterra is to let you create a lot of different individual models very, very quickly. And so the idea is, instead of having a single multi-class detector, which is what they call it in machine learning terms, what we let you do is that you can very quickly create separate detectors and then run them on the same image. So you can build a model for swimming pools, you can build a detector for rooftops, and then run them all on the same image. And you can achieve the same results as having a multi-class in that way.
Thank you. Maybe we have time for one more question. And there is a question, how can we use Sentinel on Picterra?
So Sentinel is basically, you can actually connect it to the platform by this import remote map. So actually from our website, if you go on the imagery page, you will be able to directly import some Sentinel data there. So Sentinel 2, the RGB, the false color, so some pre-established feed of imagery. If you want to get deeper into that, basically what you can do is to have a WMS service that can come from different data cubes. So it could be, for instance, Sentinel from Synergize. There's others that you could use. Then you can plug this WMS on the platform. And so it means you will be really able to control what you feed in the platform. And then when it's about building a detector on Sentinel, you could try what Roger was saying. Maybe you have access to some high resolution annotations. You could import them on the platform on top of Sentinel and try to train a model like that. Or then simply annotate most likely more areas. So with Sentinel, you're more in segmentation mode, where you could be about urban areas and looking from there about changes. So changes of urban areas expanding, things like that.
Thanks, thank you, Frank. So thank you very much for all your questions. We will have a look at them after the webinar and answer them. You will receive the recording of this session together with the Q&A session. So I hope we will answer also the rest of your questions. In terms of questions about some basics of how does it work, what's the pricing, I strongly encourage you to check our website, picterra.ch. Our blog, also the university, the Picterra University that Roger mentioned. And thank you very much. And we will be back to you. We will send you an email with everything. So thank you, Frank. Thank you, Roger, Georgia, Gabriel, and thank you.
Thank you very
everyone.
much. Thank you.
Maybe the last thing, so it's by actually really accident and chance, but exactly today it's the birthday of Picterra, so 4 years. You're a baby that now knows to walk. start to talk and start to go to school. So yeah, that's it. Happy to continue the journey with all of you, and we look forward for next webinars. Thanks for attending, and see you soon.
Thank you.
Bye-bye.
Thank you. Bye-bye.